Have you ever wondered what our universe is made of? We see stars, galaxies, and all the ordinary matter around us. But what if I told you that everything we can see, touch, or feel is just a tiny fraction of the universe's totality? More than 95% of the universe remains beyond our direct observation, hidden in the mysterious veil of dark matter and dark energy. Let's explore two of the greatest mysteries that challenge humanity's understanding of the cosmos. Welcome to SpaceTime's universe journey of discovery, where we explore the deepest mysteries of the universe. In this video, we will explore dark matter and dark energy, the universe's greatest mysteries. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us. We begin our journey with dark matter. This concept was first proposed by astronomer Fritz Zwicky in the 1930s when he studied the Coma galaxy clusters. Zwicky noticed that the galaxies in the cluster were moving so fast that they should have flown out of the cluster if only the visible, ordinary matter was holding them together. He coined the term dunkle Materie, dark matter, to describe this invisible component, estimating that it accounted for up to 90% of the cluster's mass. It wasn't until the 1970s that Vera Rubin and Kent Ford provided more compelling evidence for the existence of dark matter. They studied the rotation curves of spiral galaxies by measuring the velocities of stars and gas at different distances from the galactic center. According to Newton's laws of gravity, objects farther from the center should move slower, similar to the outer planets in our solar system. However, Rubin and Ford discovered something unexpected. Stars at the galaxy's edge rotated at almost the same speed as those in the center. This directly contradicted what classical physics predicted. To explain this anomalous rotation, there must be a large amount of additional invisible matter, providing extra gravitational pull to keep the distant stars from flying off, forming a giant dark matter halo surrounding the galaxy. So what is dark matter? The most certain thing we know is that it's not ordinary matter, or baryonic matter, the type of matter that makes up protons, neutrons, and electrons, which in turn form atoms, planets, stars, and ourselves. Evidence from Big Bang nucleosynthesis has very tightly constrained the amount of baryonic matter in the universe, showing that it accounts for only a very small fraction of the total cosmic mass. Dark matter does not emit, absorb, or reflect light or any other form of electromagnetic radiation. It does not interact with ordinary matter particles via the electromagnetic force or the strong nuclear force. The only interaction we know it has is gravity, which makes direct detection extremely difficult, like trying to catch a cosmic ghost. Some of the strongest and most visual evidence for dark matter comes from colliding galaxy clusters, notably the Bullet cluster. When two galaxy clusters collide, the hot gas, baryonic matter, interacts with each other and slows down due to drag, accumulating at the center of the collision. However, stars and dark matter do not interact strongly, so they pass right through each other. When scientists mapped the distribution of the total mass in the Bullet cluster using gravitational lensing, the bending of light from background galaxies due to a gravitational field, they found that the greatest mass was not concentrated in the hot gas region, but in areas where the galaxies were not slowed down. This indicates that an invisible mass component, dark matter, passed through the collision unaffected, separating from ordinary matter. Candidates for dark matter are diverse and are classified as hot dark matter, if the particles move at relativistic velocities, or cold dark matter, if they move slowly. Current cosmological evidence supports the cold dark matter model, meaning that dark matter particles must have significant mass and move slowly. One of the most popular hypotheses for cold dark matter is WIMPs, weakly interacting massive particles. These are hypothetical particles many times more massive than protons and only interact through gravity and the weak nuclear force. This weak interaction helps them bypass observational limits on baryonic matter and explains why we haven't detected them yet. WIMPs are predicted to emerge naturally from some theories extending the standard model of particle physics, such as supersymmetry. Supersymmetric models predict that each standard model particle will have a heavier supersymmetric partner, and the lightest among them could be a stable WIMP, serving as dark matter. Ultra-sensitive detectors like Xenon NT, LZ, and Pandex are placed in tanks of ultra-pure materials like liquid xenon, hoping to record these rare collision signatures. However, so far, the results have only been upper limits. Another candidate is the axion, a hypothetical super-light subatomic particle created to explain a problem in quantum chromodynamics, specifically the strong CP problem. Axions are thought to interact very weakly with ordinary matter and could form a significant part of cold dark matter if they are very low mass but exist in huge numbers. Experiments like ADMX, the Axion Dark Matter Experiment, are looking for signs of axions by attempting to convert them into photons in a strong magnetic field. If axions truly exist, detecting them would not only solve the dark matter problem, but also provide deep insights into high-energy particle physics. There are also hypotheses about primordial black holes, formed in the very early universe. If enough black holes exist with masses ranging from a gram to thousands of solar masses, they could contribute to dark matter. However, gravitational lensing and gravitational wave observations have placed tight constraints on this possibility. Sterile neutrinos are another hypothesis. Unlike the three known types of neutrinos that interact through the weak nuclear force, sterile neutrinos are thought not to interact with any fundamental forces except gravity. If they have the right mass and are sufficiently numerous, they could contribute a significant portion of the universe's total dark matter, though they would fall into the warm dark matter category, slightly different from cold dark matter. Indirect detection experiments look for the decay or annihilation products of dark matter. If dark matter particles annihilate each other upon collision, they could produce standard model particles such as gamma rays, positrons, or high-energy neutrinos. Space telescopes like Fermi-LAT have searched for signs of excess gamma rays from dark matter-dense regions in the universe, such as the Milky Way center and satellite dwarf galaxies. Finally, particle accelerators, like the Large Hadron Collider, the LHC, at CERN, are also trying to create dark matter particles in high-energy collisions. By colliding protons at near-light speed, scientists hope to create dark matter particles and detect them through missing energy, energy that cannot be accounted for after a collision, indicating that particles passed through the detector without interacting. After dark matter caused a gravitational mystery, the universe presented an even bigger, more puzzling enigma: dark energy. For decades, scientists believed that the expansion of the universe, discovered by Hubble, was slowing down due to the gravity of all matter. It was expected that the universe would either contract, expand slowly indefinitely, or eventually stand still. However, in the late 1990s, observations of Type 1a supernovae dramatically changed everything. Type 1a supernovae are explosions of white dwarf stars in binary systems that reach a certain mass limit, the Chandrasekhar limit, before collapsing and exploding. Because they all have nearly the same intrinsic brightness, they act as reliable standard candles, allowing astronomers to accurately measure their distances. Two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, simultaneously observed distant Type 1a supernovae. What they discovered shocked the entire scientific community and earned them the Nobel Prize in Physics in 2011. Instead of finding that distant, and thus older, supernovae were slowing down due to gravity, they found that they were moving away from us faster than expected. This meant that the expansion of the universe was not only not slowing down, but it was accelerating. This was an extraordinary discovery, challenging all previous understanding of the universe's fate and demanding a completely new explanation. The most widely accepted explanation for this accelerating expansion is dark energy. Dark energy is believed to be a mysterious form of energy, accounting for about 68% of the universe's total energy density. Unlike matter, ordinary and dark, dark energy does not clump together in galaxies or galaxy clusters. Instead, it is thought to be uniformly distributed throughout space and possesses a strange property: negative pressure. This negative pressure acts as a repulsive gravitational force, counteracting the gravitational pull of matter and causing space itself to expand at an ever-increasing rate. If dark energy has negative pressure, it means that as the universe expands, its energy density remains constant or even increases, depending on its exact nature, rather than being diluted like ordinary matter. This is key to explaining the acceleration. Hypotheses about dark energy are also diverse and complex. The leading hypothesis is the cosmological constant, originally introduced by Einstein in 1917 to keep the universe static, before he abandoned it after Hubble discovered the expansion of the universe. The cosmological constant is considered an inherent energy density of SpaceTime, an intrinsic property of empty space itself, a form of vacuum energy.
The big problem with the cosmological constant is that the value predicted by quantum field theory is vastly larger, about 10 to the 120th times, than the observed value. This enormous discrepancy is known as the cosmological constant problem and is one of the biggest challenges in modern theoretical physics, suggesting that we are missing a crucial part of our understanding of fundamental physics. Another hypothesis is quintessence, a dynamic scalar field with negative pressure. Unlike the cosmological constant, which has a fixed value, quintessence can change over time and space. This could explain why dark energy became dominant in later stages of cosmic history, once the universe had expanded enough for the density of ordinary and dark matter to be diluted, allowing quintessence to play its role. Some physicists also propose modified gravity models, suggesting that we don't need dark energy. Instead, Einstein's laws of gravity might need to be modified at large scales or at low energy densities. Instead of adding a new energy component, these theories change how gravity works. For example, F of R gravity or extended gravity theories. Current observations provide strong indirect evidence for dark energy, but its true nature remains a deep mystery. The combination of Type 1a supernova observations, cosmic microwave background mapping from Planck and WMAP satellites, and large-scale galaxy surveys all consistently point to the existence and properties of dark energy. The cosmic microwave background, CMB, is the oldest light in the universe, a remnant of the Big Bang. Tiny temperature fluctuations in the CMB, measured with extreme precision, provide detailed information about the universe's composition and geometry. These data strongly reinforce the lambda CDM model, lambda cold dark matter, where dark energy is described by the cosmological constant lambda. Large-scale galaxy surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, also provide crucial evidence. By mapping the distribution of millions of galaxies in space and measuring the growth of large-scale structures in the universe, scientists can measure how the universe's expansion has affected the formation of galaxy clusters, confirming the accelerating expansion and the role of dark energy.
Currently, the standard cosmological model, or the lambda CDM model, suggests that our universe consists of about 5% ordinary baryonic matter, atoms, protons, neutrons that we know and interact with, 27% dark matter, and 68% dark energy. This figure shows that we only understand a very small part, about 5%, of the universe we live in. The existence of dark matter and dark energy is a major challenge for modern physics, considered two of the most important unsolved problems. It implies that our understanding of fundamental physical laws, from quantum mechanics to general relativity, is still very incomplete or needs significant expansion. A revolution in physics may be awaiting us, just as Einstein's theory of relativity completely transformed Newtonian physics in the early 20th century, or how quantum mechanics ushered in a new era of understanding the subatomic world. Deciphering these mysteries could lead to entirely new physical theories. Unraveling dark matter and dark energy will not only open the door to a deeper understanding of the universe's composition and dynamics, but could also reveal entirely new physical laws, fundamental particles never before known, or even a different nature of space and time that we have never imagined.
Ambitious future projects are underway to continue searching for and analyzing data. The James Webb Space Telescope, JWST, is observing early galaxies, helping scientists better understand the formation of large-scale structures in the universe under the influence of dark matter in the earliest epochs of the cosmos. The Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST, will create the most detailed 3D map of the universe ever in a decade. This data will be extremely important for studying weak gravitational lensing, a powerful tool for mapping dark matter distribution and understanding how dark energy impacts the evolution of cosmic structures. Many other particle physics and cosmology experiments are also planned, including next-generation dark matter detectors with higher sensitivity, ground-based and space-based dark energy surveys, and gravitational wave search missions to test modified gravity theories. Each project is a piece in the larger puzzle. The study of dark matter and dark energy is not only a task for theoretical physicists and astronomers, but also an intellectual adventure for all humanity. It reminds us of our humility before the vast and profound mysteries of the universe, and it drives us to continually ask questions and seek answers.
Every small step forward, whether a new upper limit in dark matter detection or a more precise measurement of the universe's expansion rate, is a leap for science, pushing the boundaries of what we thought was possible. From deep underground laboratories to distant telescopes in space, a global effort is underway to decipher these invisible components. Although there are no final answers yet, The journey of discovery has itself brought incredible findings and reinforced faith in science's ability to tackle the toughest challenges. We stand at the threshold of revolutionary insights into the fundamental nature of the universe and the laws that govern it. The existence of dark matter and dark energy is a profound reminder that there is still so much we don't know about the universe. Over 95% of its composition remains a big question mark, an unending invitation for curiosity and exploration for future generations of scientists. These mysteries do not discourage us. On the contrary, they motivate us to dig deeper, ask bolder questions, and develop more sophisticated tools to unveil them. The quest for answers is a testament to humanity's enduring scientific spirit and desire to understand the world.
And as we draw closer to unraveling these mysteries, we not only gain a better understanding of the universe and how it operates, but also of our own place in the grand tapestry of cosmic events. Each discovery is another piece added to the grand picture of existence and origin. The journey of cosmic discovery is an unending one, where each answer opens up a myriad of new and more complex questions. That is the endless beauty and appeal of space science, a field that never runs out of things to explore. Together, we are weaving a broader tapestry of understanding, one thread at a time, one mystery at a time, about the universe and its invisible constituents. And this journey, without a doubt, will continue to bring new wonders and challenges. Dark matter and dark energy show us that the universe holds many mysteries, far beyond what we can see. But is there a more fundamental mystery about ordinary matter itself? If the Big Bang created matter, it must also have created antimatter in equal amounts. So why is our universe predominantly matter, and where has our antimatter seemingly disappeared to? In the next video, we will explore matter and antimatter. Why does the universe have more matter